In this section, we will see the definition of a determinant. There are several equivalent definitions. You are invited to open Wikipedia and to see the page determinant. Very useful information. Let me give you one possible definition of the determinant using minors and cofactors. If we have a matrix A, say 3 by 3 matrix, say 1, 2, 0, 3, 1, 1, 0, 2, 2. Then, if you choose one row and if you choose one column, then if we delete this row and this column, we get a smaller matrix, and the determinant of this smaller matrix is called minor. So if we choose, say, I is 1, j is 1, that means we choose this position, and when we delete the first row and the first column, then the minor n11 is the determinant of this smaller matrix, 1, 1, 2, 2. So, minor is the determinant of a smaller matrix when we delete one column and one row. If we multiply by plus or minus 1 in this scheme, then the resulting product is called cofactor. Minus 1 to the power of I plus j is just plus or minus 1, and it can be visualized by the following checkerboard structure. And it can go further this way. Because this position at the top on the left corresponds to I is 1, j is 1. Then I plus j is 1 plus 1, which is 2, and minus 1 squared is plus 1. That means we write plus. And if you move one position to the right, or if you move one position down, then this exponent, I plus j, changes by 1. And if the exponent changes by 1, then from an even exponent you get an odd one. And minus 1 to an odd integer is minus 1. That's why we have minus and minus here. And once again, every change, every step in this structure, either to the left or to the right, or up or down, changes the exponent from even to odd and vice versa. So as a result, this coefficient changes its sign. So you don't have to compute this minus 1 to I plus j if you think this checkerboard structure. So minor was the subdeterminant. When multiplied by this factor, this is called a cofactor. And determinant of a matrix can be defined in terms of determinants of smaller matrices. This makes sense because for a 1 by 1 matrix, this is the entry 1 by 1, A11 itself. And if we take this as the first step in the definition of the determinant, then this can be a way how to define a determinant of a 2 by 2 matrix in terms of a determinant of a y by 1 matrix. Well, and if we have 2 by 2 matrix determinant, this can be used to define a determinant of a 3 by 3 matrix in terms of determinants of a 2 by 2 matrix. This is sometimes called recursive definition, which makes perfect sense. Well, what does it mean? Here we choose one fixed j between 1 and n. That means we fixed one column. Say column number 3. And then for each I from 1 to n, we consider all the entries in this chosen column. And we consider means we take the entry on the position ij. J is fixed. This is the third column or any column. And I is the running index that runs from 1 to n, the dimension of the matrix. And we multiply the entry by its cofactor, which is this and which is this. And we multiply this and we sum all these entries, and the resulting number is the determinant. We can choose any column. Anyone will do, hopefully giving the same result. Or, equivalently, we can choose any row. If we choose a column, we say we expand the determinant along a column. Or, equivalently, we can expand the determinant along a chosen row. Any row will do. So here we have I fixed between 1 and n. If we fix I, that means we fix one chosen row. And then we run along this row from the left to the right. That means j goes from 1 to n, and the same computation. We consider each entry on the chosen row, and we multiply by the corresponding cofactor given above. Okay, let us illustrate this procedure for this chosen matrix. So let's start with the first. Let's start with the first row. Let's start with the first column. So we fixed first column, and determinant of this matrix is then A11, which is 1, times determinant 1, 1, 2, 2. Then we move to the next entry in the chosen column, which is 3, but we must multiply by -1. And the minor is determinant of this matrix when we delete the first column and the second row. So what remains is 2, 0, 2, 2. And then we go to the last entry in the first column. It's 0, so everything else is completely irrelevant. But for the pedagogical purposes, let me complete this. If we remove the first column and the third row, we are left with the submatrix 2, 0, 1, 1. And this is the determinant. Well, we know from the previous section that the determinant of a 2 by 2 matrix is this times this minus this times this. So let me complete this. Actually, we can verify this rule separately using this definition before we use it. So if we have a matrix A, B, C, D, or if you like A11, A12, A21, A22, then determinant of this matrix, if we expand this matrix, say along the first column, so this is this entry times this subdeterminant. But the determinant of a 1 by 1 matrix is the entry itself. Plus -1 times C times the minor generated by deleting the first column and the second row, which is B. And you see, this is in perfect agreement with our definition before, AD minus BC. So this is indeed the way how to compute the determinant of a 2 by 2 matrix. Well, we can expand this along the second column. Minus B times the subdeterminant, which is C, plus D times the subdeterminant, if we cancel the second column and the second row, A, which is again AD minus BC. Or if you like, we can expand this determinant along the first row. A times the subdeterminant, which is D, minus B times the subdeterminant, which is C. Or, to have the complete picture, we can compute the determinant by expanding along the second row. C, but minus, because of this, times the subdeterminant when we delete the first column and the second row, which is B, plus D times the subdeterminant generated by deleting the second row and the second column, which is A. And again, well, this is A, AD minus BC. So we have 1 times 1 minus 1, which is 0, minus 3 times 4, plus 0, which is minus 12. Let's try the third row, for example. That was one. That was along the column. Let's try the third column. Hopefully to get the same result. So here is the third column. It has these 3 entries, and for each of them we multiply the entry with the cofactor and we sum all these contributions. So we start with 0 times the determinant 3102. Well, this is not important because we multiply by 0, but just to understand how it works. Plus, minus 1 times, and when we delete the second row and the third column, we get the determinant 1202. And finally, plus 2 times the determinant when we delete the last row and the last column, and what remains is 1, 2, 3, 1. So this is 0. Here we have minus 2 plus 2 times 1 minus 6, which is minus 5, which is minus 10, which is minus 12. Yeah, the same result. Or, so that was expanding the determinant along a chosen column. Let's try expand the determinant along a chosen row. So say if we choose the first row, I is 1. We have these 3 entries, and we consider each of them, and we multiply by the cofactor, which is this plus or minus 1 times the subdeterminant, the minor. So we start with 1. Times the determinant that we get when we cancel the first row and the first column, which is 1, 1, 2, 2. minus 2 times, minus because of this. And the subdeterminant, when we delete the first row and the second column, is 3102. And finally, plus 0 times 3102. So this is 2 minus 2, which is 0, minus 2 times 6, plus 0, which is again minus 12. So once again, we can define and we can compute the determinant of a square matrix by expanding along a chosen row or by expanding along a chosen column. Any row will do, any column will do. While in practical computation, we often choose such column or such row where there are many zeros. That's convenient. And then for the chosen row, we consider each entry and we multiply each entry by the cofactor. Cofactor is the minor, the determinant, generated by deleting the ith row and the chase column, multiplied by minus 1 to the power of I plus j, which is plus or minus, which can be found from this checkerboard structure, starting with plus in the top left position. The matrix must be a square matrix, otherwise the determinant is not defined. Well, this notation with the vertical bars is dangerous for 1 by 1 matrix. Very dangerous situation. If you write then both results are correct, just it has different meaning. Here, the vertical bars mean absolute value. Yes, absolute value of a negative number is a positive number. Absolute value of minus 3 is plus 3. This is also correct, but this time the vertical bars do not mean absolute value, but rather they mean the determinant of the matrix. And this is a 1 by 1 matrix, and its determinant is the number itself. To avoid this confusion, I would rather omit this writing, and I would write A is minus 3, and then determinant of A is minus 3. I would write it this way to avoid this unpleasant situation. It's always a problem if we have one graphical symbol for different meanings, and it appears sometimes in mathematics, unfortunately. And in the next chapter, we will discuss determinant in more details.